Welcome to the relay lab at Electrical Engineering Department, IIT Kharagpur, India. In this laboratory, we will be demonstrating you few laboratory experiments on power system relays. We have a team, Mr. Amitabh Nandi, Mr. Anupam Pandey and Mr. Subhadeep Paladi and myself Professor A. K. Pradhan. We will be demonstrating you experiments on overcurrent relay, directional overcurrent relay, differential relay and distance relay in this lab one by one. In the experimentation, we will show you the circuit, we will element wise on the table we will show you that which one is connected to what, followed by we will show you the details on the particular numerical relay and how the corresponding settings are being obtained. These relays are connected to the PC through which you can have the corresponding settings. Then we will create faults in the circuits like the fault in a power system and how the corresponding relay trips the corresponding circuit breaker and isolates the corresponding faulted section, faulted part of the system, and then the corresponding recordings will be seen in the PC. So, we will take several observations like that and we will plot them corresponding observations and we will compare that corresponding observations with a standard relay characteristics available in that particular relay to which it is being used at that time. By this way, we will be verifying the corresponding relay performance during different settings and system conditions. So, this will enrich us in learning the corresponding relay characteristics or the principles while protecting a power system. Now, we will go to few slides before proceeding for the experimentation. In addition to the 4 relay experiments, we have the PMU experiment also, which provides us the insight of the synchrophasor technology, and we will have an applications oriented and demonstrate how the corresponding PMU measurements are being carried out in the power system applications. Note that our here the experimental verifications in this laboratory will be based on the corresponding without the injection kit, which generally the corresponding engineers use relay injection kit for this different testing of the relays, but to make it more lively and so in differential relay experiments for the transformers we will have create real transformer internal fault and external fault, and in case of distance relay also we have transmission system where we will create a actual fault and so. So, and in case of the PM also we will have the real transmission system models and then the actual PMU connected being to the systems we will have these corresponding measurements and observations. Our focus here will be that how the corresponding for the observations and a feeling on the experimentation perspective in a real environment of the different relays. For that we have a special arrangement for the purpose. So, we have first the demonstration on overcurrent relay. So, we will verify this overcurrent relay characteristic, particularly as we have learned in the theory on the here we will be demonstrating one characteristic on the inverse definite minimum time IDMT characteristics widely used in power system different applications. So, for this we have the objective is to verify the relay characteristics. We mean by that the characteristics set in the relay for a specific type like IEEE curve and so, we will pick up that characteristics and then through this our experimentation for different loading conditions, different fault condition, fault current versus time, we will obtain the required time of the trip by the relay, and then through that we will try to verify that whether the relay is performing as per expectation or not. We have a circuit diagram for this demonstration to create fault and the corresponding current through the CT connections to the relay. That circuit diagram we have, and then we have the theory, that theory which we have already learned in the for overcurrent relaying theory. And then you can say that we have the settings through this relay. We will have the different settings which is required, like in the overcurrent relay we have pickup setting and we have time multiplier setting and so. And then we will take several observations to make a conclusion whether the relay is performing as expected or not. So, for this we have the objective is to verify the operating characteristics of this numerical relay, and our numerical relay which will be through which we will be demonstrating this is the MICOM P154, and that is of Alstom make. Now, we have a circuit diagram where we have a source of 110 volt and then we have a auto transformer. This auto transformer gives us variable voltage single phase output, and then we have a resistor 5 ohm 9 ampere, and through which you can say that to which you can say that is the corresponding current is being fed from the auto transformer. This current through a CT connection, we have the corresponding current. CT secondary is being connected to the MICOM relay, and this you can say that MICOM relay, it takes you can say that input you can say that for its operation 110 volt AC supply. Now, the relay takes a decision, and this you can say that decision is being fed to the corresponding the decision is being fed to the corresponding circuit breaker, the contact here. So, these are breaker here, and this you can say that the corresponding breaker for the trip circuit takes a 220 volt AC supply. So, what I do here that the corresponding current through this resistor can be increased by increasing the voltage from the auto transformer, and that you can say is being sensed by the CT, which you can say that is fed to the corresponding relay. The relay is being considered set with a particular pickup setting, and then when the corresponding injected current through the CT secondary to the relay exceeds that, so you can say that pickup setting, the relay trips. And in this case we have set an IDMT characteristics. So, therefore, it follows that characteristics that curve, and when the current becomes higher, the time we can say that of decision becomes smaller, and that is what you can say that we like to notice from our set of observations to the experimentation. So, by this way you can say that this faulted circuit, these are you can say that emulation of the faulted circuit path. So, through which you can say that a voltage injection happens to be there, which changes the level of current through the circuit, and that level of current you can say that through the sensors of the CT, the corresponding relay senses that corresponding fault situation, and then it accordingly makes a trip decision for that perspective. Now, this relay in this case you can say that we have picked up this IDMT characteristics, and that you can say that we have picked up this IEEE moderately inverse characteristics. So, in general you can say that the corresponding T follows the equation of capital T into k upon I upon I s to the power alpha minus 1 plus L, and then you can say that we have the corresponding theory behind this, which is already there in our theory part. So, k becomes the coefficients in the table, and this you can say that curve can be considered from any curve selected from the variety of things which are available inside the relay, and it is IC curve. It can be the IEEE or US the ANSI you can say as you call, and then you can say that the corresponding I is the value of the current which is being injected through the relay through the CTs, and then IS is your pickup current, alpha is the coefficient as in the mentioned the table, alpha, L and K, and then you can say that the L and T you can say that the T the time multiplier setting between 0.025 to 1.5 particularly for this in this relay. Now, in furthermore we should note also that as already defined in the theory, clock setting multiplier, the PSM happens to be considered the relay current injected upon you can say that the corresponding set current or the corresponding pickup current. So, that how many times of the corresponding PSM we are injecting to the consider that to the relay for operation, for its operation, that matters to us in our observation perspective. So, TMS here stands for the time multiplier setting. Now, in the setting perspective, we will have the corresponding different relay settings, and then you can say that we will proceed for this the observations and demonstration part. So, we will verify this relay characteristics. Our relay is P154 Alsthamic and this is a P50 agile series. Now, to test the relay, we have a small power system which injects the required current for this overcurrent relay setting. So, our system consists of an auto transformer which provides us the required voltage. The auto transformer output injects currents to this resistor. So, the resistor is connected in series to this circuit and that closes the circuit. So, when you go on increasing the corresponding voltage through the auto transformer, the current through the resistors increases, and that is our power system which emulates to the distribution system or transmission system for which the corresponding overcurrent relay is being used. Now, this overcurrent relay takes the signal for this small system through the CT. The CT primary is connected to, you can say that the 10 ampere side to this circuit, and the CT secondary of 5 ampere is connected to the you can say that to the relay side through the wiring. Now, this clamp meter is connected to the primary circuit, and that gives us the reading of the how much current is being injected, how much current is being there in that fault path circuit, so called fault path circuit, that is through the resistors injected from the auto transformer. The corresponding circuit will be tripped, will be isolated when the relay commands, that is the output of the relay trips the corresponding breaker, and the breaker you can say that arrangement is done here. So, this breaker receives the corresponding signal from this relay, and then whenever the current exceeds, the relay trips, but the relay trips the breaker, but the relay takes its own time, because here we have a setting, we have gone for this IDMT characteristic curve as already mentioned, and through this we can say that we will go for the demonstration. In addition, this relay takes voltage for its operation 110 volt supply from this side, and the relay is connected to the PC for different settings and taking the observations as recorded by the relay. So, this PC connects the corresponding to the relay. To this you can say that PC and monitor arrangement, we can see the different observations for this perspective. So, whenever you close the corresponding supply to the system, the auto transformer feeds voltage to this particular circuit, and then you can say that the current being set, you can say that as per the clamp meter here. So, knowing this corresponding current, we allow the fault current to continue, and then the fault current exceeds the corresponding pickup setting, the corresponding breaker opens after some time depending upon the relay characteristics, and then you can say that the corresponding faulted circuit is being isolated. So, in next step we will demonstrate the corresponding fault perspective, and before that we will tell about the corresponding settings of the relay. So, now we will see the relay details. If you see the front panel, this P154 overcurrent relay. So, we have on the front panel, we have different setting arrangements. For that you can say that we have different keys, and then we have a display, you can say that portion through which you can see the currents, the corresponding settings, and so. In this front panel we can see also, you can say that the relay is on or off state. So, whenever you give supply, you can say that to the relay, it can go to the on state. Then whenever the fault triggers, then it starts, and finally, when the corresponding relay makes a trip decision, the trip we can say that symbol will be, can say that through the LED will be activated here. Now, these are the front, if you see this, you can say that connection, this connection goes to this PC connections or to your laptop, through which you can say that we can change the different current, time and all setting perspective, different characteristics and so. And also you can say that we can read the corresponding recorded relay, you can say that recorded things like for the fault, you can say that history and so in the PC. So, we will see that part also. So, if you see this connection diagram for this relay, so we have 3 phases, R phase, Y phase and V phase. So, these are the connection for this through the CTs, you can say that to the 3 phases the connection, and also you can have the connection for the earth fault, you can say that the corresponding neutral wire connection also, and another you can say that through the another CT you can connect also. Now, in addition to this, you can say that 4 current inputs to the relay, we have opto isolated binary inputs also, as already you can say that understood from our theory that any numerical relay can have, you can say that have information from other relay also. Through this you can say that you can have input, and the output you can say that of these corresponding relays are being considered from these you can say that part of the circuit. Now, if you see the you can say that back side, the corresponding connections you can say that details are given. So, from the manual of the you can say that this particular Alstom relay, we can have you can say that different connection ports you can say that as per the wiring diagram, and from that you can say that we can have the corresponding input to the relay, output of the relay, and different you can say that the corresponding relay connections from the CT you can say that connections, and all these details are provided at the back of this one. So, this you can say that is all about the connection perspective of the particular relay. So, in this overcurrent relay experiment, we will have few settings. On that setting perspective, we have the corresponding things on the relay backup setting of 1 ampere. We have first fixed it on 1 ampere, and this setting on current is on the primary side, both pickup current setting and the corresponding the current which will be observed, we can say that in the particular relay. So, when we say can say that primary side means it is CT primary. So, CT primary is nothing but connected to the system side, the power system side, for which the relay is being connected to protect. We have a time multiplier setting of 1 second here, which is also we can vary, as we have already seen, you can say that we can have numerous options on that. And then the characteristic curve which we have picked up is on IEEE moderately inverse curve. We have numerous curves as already mentioned in the our table, last table also, and also we have seen from the relay that there are numerous you can say that curves, characteristic curves available. One of the you can say that reasons for why it is available, that whichever curve best fits to a particular requirement, that has to be there, and then you can say that that you can say that also whichever curve we have picked up, accordingly the coordination also is to be obtained. Now, the CT ratio which we have you can say that taken here, even though you have numerous connections variable available, but we have you can say that our CT picked up here is 10:5. I will tell you why you can say that the 10:5 is there. If we take you can say that 50:5, 25:5 and so, then what happens that the ratio becomes larger, and the current requirement to actuate the relay becomes larger and larger current at the system side. So, in a laboratory experiment, if you have you can say that 5 PSM, 10 PSM and all these things, the level of current requirement becomes enormously high, and that for that you can say that it requires special arrangement, special cable and so. To overcome that problem, the CT ratio is intentionally taken to be lower. One point here that sometimes you can say that to have more you can say that PSM value in experimentation to verify the characteristic of the relay, you can take the corresponding CT connections the other way also, that is 5 ampere side to the system side and 10 ampere to the relay side. By that way the current is being amplified. That helps you can say that injecting more amount of current with less amount of burden to the system side, and that is for you can say that the testing of the relay in the laboratory. But in practice as already understood that the purpose of CT is to downscale the current. So, here for the demonstration the corresponding system side current when it happens to be 10 ampere, the corresponding relay current will be 5 ampere. So, we have taken a 10:5 ampere CT ratio for this perspective. Now, the relay current you can say that and the curve which follows you can say that the IDMT modelling curve is this, and we have already you can say that are aware of what is the corresponding k value, alpha value and the L value for this. As already mentioned, the IS you can say that the pickup setting you can say that here is 1 ampere and the corresponding T you can say that time multiplier setting is 1 here. So, now you can say that if you see already you can say that shown in the relay setting first you can say that one, we have you can say that a current setting of 1 ampere as I mentioned, we have seen in that one also, and then you can say that the time dial also is 1. In this case you can say that you clearly see here in terms of that. And on the function perspective, we have 3 functions, 3 relay functions can be used. You can say that the relay can perform 3 relay functions simultaneously. So, we have taken you can say the first one, and the only one you can say that we are testing for our purpose, the application perspective. So, we have used you can say that IEEE moderately inverse characteristics for this demonstration. So, we have for this particular relay MICOM Agile software. Now, we will see the how the corresponding settings start to be obtained and how the corresponding recordings can be seen through the PC. So, entering into this software for the compatible to this particular relay. So, if you go to this P154 module, so we are connecting to that. So, now from this we will go to the setting. So, in the settings we see here you can say that P50 Agile P154 series, our relay is of that. So, we will go to the configuration, and the configurations will go to the setting. So, this corresponding current and the corresponding pickup setting we are going for the primary as already shown here. So, we are setting for the primary side. So, both options are there, you can do in the relay side, that is secondary of the CT, or you can do on the primary. So, we are going to the primary side. So, our the corresponding emitter reading through the clamp meter will be compatible to that is connected to the primary side as already mentioned. So, here as the data input you can say that here as already shown in our circuit diagram and also in the CT connection already made is for 10 ampere at the primary side and 5 ampere at the secondary side, and this 5 ampere you can say that is connected to the current connected to the relay. So, here already seen you can say that the 10:5 I can say that CT is being connected for this arrangement. Now, we are going for the next about the 3 functions available. So, for the relay, so simultaneously it can operate these 3 functions. So, the first function we are using only to demonstrate this inverse definite minimum time. So, IEEE medium inverse you can say that curve we are picking. You can have all these varieties of you can say that the corresponding relays relay characteristics which we have already shown in the table you can say that for the particular relay. So, here we are just picking up for the IEEE M inverse, but you can also take any other curve for any testing of the relay. So, going to this one. So, this first one we are going. So, here you can say that for the relay settings we need essentially the pickup current setting. So, pickup current setting is the first one you can say that is 1 ampere we have taken, and then which has a range of 0.5 to 40 ampere perspective. This is all to the primary side, to the power system side. The relay you can say that time dial setting is of 1 and which can have a consider very small value of 0.01 to 100, and this is the beauty of the numerical relay. Now, this is all about you can say that setting. We can see also you can say that after the demonstration about the how we can go for the recording perspective and so. So, now we will have the demonstration for this experiment. So, first we will see that once we inject current through this auto transformer to the circuit, power system circuit to the faulted path circuit, how the corresponding relay sees the current through the CT. So, that we will first verify. So, the relay current is obtained can be seen from this PC monitor, and the circuit you can say that current will be through this clamp meter. So, let us you can say that we are the circuit is already connected. So, we are increasing the corresponding current through the circuit, and the current you can say that we have set now in this clamping ammeter is let us say here 1.3 ampere. So, if you see here you can say that the clamping ammeter shows clearly is 1.3 ampere. Now, what you see from this through the monitor, if you see you can say that the corresponding reading you can say that little bit dynamic, you can say that changing due to the voltage little variation. So, the corresponding primary side you can say that current what is being shown here you can say that is from 1.383 ampere, and so therefore, you can say that we say that the primary side current recorded by the clamp meter and that of the can say that relay currents are matching. So, therefore, the relay you can say that gives us the primary current, also the secondary current, as you see you can say that here the secondary of the can say that the CT gives you can say that is 10:5 you can say that. So, it is a factor of 2. So, this 1.383 divided by the corresponding 2 you can say that gives you the 6 point you can say that around 7 ampere of current at this particular moment, and so. Now, this shows about the current perspective. Now, what we will do, we will create you can say that fault, and the corresponding relay is set at you can say that 1 ampere pickup current and 1 TMS, and based on that you can say that the relay will go for the trip command. Now, upon this you can say that we will have the current different settings, and then you can say that the relay will go for the trip command. So, now let us say you can say that we have a based on the PSM is the relay current upon the corresponding pickup setting. So, one you can say that PSM is a very large very high you can say that the time you can say that required for the trip, and so. So, we will go for you can say that more than you can say that 1 PSM. Let us say you can say that we are target for you can say that 2 PSM to have a verification. So, 2 ampere of current you can say that we will inject, and then see you can say that how much time the corresponding relay will go for the trip decision. So, first you can say that we will go for the 2 ampere setting through this one, and then you can say that see the corresponding setting, and what we will do here that once you set the corresponding circuit to the you can say that this here if you see you can say that now here we can say that a particular current setting, the current showing here you can say that is almost 869 around 1.9 ampere, very close to the 1.9 PSM, and for this you can say that the circuit is closed now, and the relay is expected to can say that to function. So, you see here you can say that the bulb glows, and you can say that we have the corresponding trip you can say that red symbol here. So, this the relay you can say that successfully trips, because the pickup setting is 1 ampere and the corresponding you can say that current was flowing around 1.9 ampere. So, for this you can say that the observations we can see the corresponding recording you can say that. So, for this you can say that we see here you can say that the corresponding time you can say that is also mentioned here, and the corresponding recording here you can say that we see here 1.94 ampere and the corresponding trip time you can say that is 17.775 second, and you see here you can say that the corresponding the negative sequence current and the positive sequence current that will be considered 1/3 of that one comes out to be 0.62 ampere. So, the corresponding recording you can say that by the corresponding relay is also in agreement with the what we are getting from the power system circuit current perspective, and so. So, like this you can say that you can have another demonstration next. So, now we will go for a higher level of current, and we see you can say that for the higher PSM value, and the current happens to be 3.117 ampere. So, more than 3 PSM, and the relay trips as you can say see here also notice from this corresponding the trip you can say that signal at the relay point also, and on the circuit breaker the bulb flashes also. So, this shows that the relay successfully trips this circuit. We will see the corresponding you can say that the history you can say that for this also, and if you see this you can say that perspective, then we see clearly here you can say that for this 3.16 ampere the relay you can say that takes a time of 6.625 second you can say that for this one. The corresponding positive sequence current is 1.02, so also the negative sequence current 1.02. Note that this current we are injecting to phase A only. So, this is a phase A to ground fault kind of thing emulating that you can say that, and therefore, you can say that the positive sequence current happens to be negative sequence current for this fault analysis perspective. And similarly, you can say that such observations are taken, and then we will proceed you can say that for verification of the characteristic of the curve for different PSM value on x axis and on y axis is the corresponding time for the time of operation by the relay. So, after taking the corresponding observation for numerous cases, these are you can say the different sorts, different times you can say that we have a list of you can say that measurements. This is the history you can say that is collected from the particular relay, and this history table you can say that reveals that this recording 1044, 1045, 1046 through 1073 and onwards. What we say here that this recording gives us you can say that on that the corresponding time, trip time 9.260 second, and then the corresponding you can say that the IA current, phase A current happens to be 1.36, and the corresponding the negative sequence current happens to be 0.42, almost 1/3. You see here the 1/3 of that, because it is phase A to ground fault, and that consider of the consider that the positive sequence current becomes also same as the negative sequence current perspective. Now, what you see here from that, these you can say the list of you can say that points are you can say that are being tabulated you can say that like this, and this you can say that the see table you can say that we have. So, fall time and the trip time, this is what important for us for our characteristic verification. The phase A current, phase B current and phase C current, we have not injected any phase B and phase C current as in the circuit we have seen, and so therefore, you can say that this even the corresponding you can say that relay is for a 3 phase relay, and this is you can say that for the phase relay, not the ground relay we are testing. So, the corresponding one of the phases you can say that particularly phase A here is having the fault current. So, therefore, you can say that the phase A to ground fault analysis hold goods here, and in that case the positive sequence current happens to be the negative sequence current happens to be the same as the 0 sequence current. So, as already mentioned for this you can say that let us say a demonstration here that the trip time of 1.645 second corresponds to you can say that a current corresponding to a injected current of 5.34 ampere, when the corresponding negative sequence current and positive sequence current happen to be considered 1.76 ampere perspective. Now, based on this you can say that this you can say that phase relay using the fundamental component of current, and so it follows the corresponding curve here, where you can say that we have this k equals to 0.0515 and alpha equals to 0.02 and L equals to happens to be 0.114. Now, the T you can say that the time multiplier setting happens to be T equals to 1, and the injected the pickup setting current happens to be I s equals to 1 ampere. The city ratio you can say that happens to be 10:5. So, we can say that we have a 5 ampere city secondary current. So, the current is being downscaled by a factor of 2 from primary to secondary. Now, for this you can say that mark you can say that current case where the corresponding injected current is 5.3 ampere. So, 5.3 ampere you substitute here you can say that, and k becomes equals to this value and alpha becomes this and L becomes this. By substituting the value for this current, the other things are being fixed for the particular curve, moderately inverse curve for the IEEE you can say the characteristics. We see that the T computed from you can say that from this observation is 1.625 seconds for this perspective. Now, this you can say that we have demonstrated you can say that in our theory part in the NPTEL course on overcurrent relaying perspective also, how to calculate from you can say that the different characteristics for the particular relay current observed by the relay. Now, in the experimental things which I already demonstrated for this case, so the recorded you can say that time you can say that happens to be T equals to 1.645 second for this case, 1.645 second. So, we see you can say that theoretical calculation says 1.625, and the corresponding relay you can say that shows us you can say that 1.645 through our observations. Now, from this you can say that demonstration we can conclude that the corresponding experimental current experimental time for that particular PSM value or the current value, the theoretical you can say value which the relay follows you can say these characteristics happens to be there to be almost same. So, this clearly shows that you can say that the relay is following the required characteristics which is being set inside the relay for that particular characteristics. So, after summing up all these sheets you can say that which I showed in the table, we plotted those you can say that observed points, and also we plotted the corresponding reference curve, and the reference curve is obtained from that particular IEEE curve equations with k equals to this and L equals to this and T equals to 1 you can say setting here for a pickup setting of 1 ampere. Now, by this way you can say that the solid line you can say that is our reference curve from the standard IEEE curve, and the star points are nothing but are the observed point you can say that from the verification of the circuit, and this shows you can say that how close you can say that are these you can say that to observation point and the reference curve, and that demonstrate that you can say that our experimental setup through which we are getting the corresponding time of recording by the relay and the theoretical curve, they do match, and that justified that the relay performs correctly, accurately as expected. So, the verification clearly demonstrated that relay is a proper relay, is functioning perfectly as expected. Now, we have, you can say that change the corresponding TMS to 0.5, and then you can say that we have a second curve now, and you can say that the corresponding TMS equals to 0.5, you can say that implies that now the corresponding time which we are getting multiplied by a factor of half now as compared to the TMS equals to 1, and then again we repeat the corresponding experiments for several observations, and we plotted, you can say that these green dots, you can say that are the experimental plot for, you can say that 0.5 set rating. And considering the TMS equals to 0.5 for the second case, we have the reference curve from the same moderately inverse IEEE curve characteristics, and then you can say the solid line, you can say that through this, you can say that is for that reference line, and then you find this, you can say that this one. Now, at any point you can say that if we compare this, you can say that this, you can say that happens to be almost, you can say that the factor of half. So, that you can say that clearly demonstrate that that the corresponding relay is also performing at a different TMS also as expected very correctly. Now, this you can say that helps these kind of curves helps, you can say that help in the corresponding coordination aspect with overcurrent relay between different relays as backup or as a primary. That you can say that we have already learned from our earlier theory perspective in the overcurrent relay setting perspective.